Hello, welcome to chapter 1.1, part 3, which is composition of functions, more applications of function, and also symmetry of functions, more about how graphs of a function look like. So first, compositions. So if I have a function f, f. This book is a little strange in that instead of FOG, which is fog, they use GOF, which is golf. Okay. So if I have a function f, I would start off with the input x, and I use function f to get my output f of x. Remember, the function notation is f of x is the output. And then I will use this answer, and I'll use another function called g, and I would get a output g of having this as the input f of x. So this is the input for g, but the output for f, right? So input into g, and then I have g of f of x. So it's kind of like a two-step process. You start off with x, and you end up having a f of x in the middle, and then a g of f of x at the end. So this whole thing from x to g of f of x is called g of f. Notice how the order switch. You start off actually using the f function. So you use this one that is closest to x, and then you use the g function to calculate. Okay, so remember when you use, we call this composition of functions. When you evaluate this, you look at x, which is the input, and then you look at outside. Oh, I go to f first, and then I go to g. Okay, so this is the order. And if you have FOG, which most books has, then you go to G first, and then you go to F. So this is a diagram from the book that tells you, in terms of domain, what is the domain of this new function? If you start off with x and then end up with g of f of x, is the domain would be all the f that are in the domain of g of x. Okay. So because you don't want to start with some x that would not be in the domain of G, f, no, domain of g. Okay, so let's do some calculation of finding GOF or FOG like that. Okay, so function composition. So for example, f of x is 2x plus 3, g of x is 6x squared minus 4x plus 10. We want to find GOF of 1. This just means that I start off with 1 and I use f to get an intermediate answer. So I would have g waiting outside and I just do f of 1. So f of 1 is what? That means I plug in 1 here, so it would be 2 times 1 plus 3. And g I haven't done, so I just keep on writing g, and I would say 2 times 1 is 2, 2 is 5. So that's the intermediate answer for g of 1. Now I want to put this 5 into g. So I would put this 5 as an input into g. It would be 6 times 5 squared minus 4 times 5 plus 1. Oh, that's really big. So it is 6 times 25 is 150, right? Minus 4 times 5 is 20, and then plus 1. So 150 minus 20 is 130, so it's 131. Okay, or you can use a calculator to do it. What's the next one? I also want to do GOF of x. Don't have enough space here. GOF of x. So now I don't have a number, but I have f of x. F of x is what? Is this whole thing. So I would write g of 2x plus 3. That means this whole formula is now going to be input into g. So I would do 6, 2x plus 3, square minus 4. That's the input is 2x plus 3. Not just 2x, but 2x plus 3, and then plus 1. And if you simplify it by expanding everything out, so this would be 4x squared plus 2 times 3 is 6x plus times 2 is 12x plus 9 minus distribute x minus 12 plus 1. And after you simplify, it would be 24 x squared. How many x do I have? I have 72 and then minus 8. Okay, what is 72 minus 8? 72 minus 8 is 64. What about numbers? So I have 54 minus 12 plus 1. 54 minus 12 plus 1. So that is 43. So that is g of f of x. So f of g of x, maybe we'll do it in class. Okay, there's not enough space here. So let's do this part, which is application of composition of function. Oh no, actually I think I have skipped something, which is the function decomposition, which is very important. So we know we can compose two functions. What happened is later on in chapter 3 chapter 3, when we actually doing derivative of a function, we like to decompose a function into two functions in two steps. So for example, I have h of x is actually a composition of two functions. I do square root of 6x minus 5. So how can I split it so that I have an inside function? That means the first step I do is g of x, and then my next step is f. So what I can do is, you can see how this is inside. And in the square root function, that is very descriptive. This is inside. So maybe what I'll do is I would let g of x is just really the inside. That is equal to 6x minus 5. So that means I start up with, you can imagine you start up with x and you get 6x minus 5. But how come I would have a square root of it? Oh, I can define f of x is just square root of the input. Now, not square root of 6x plus 5, but square root x, because that is the input. You would square root these things, right? So that is how you define g and f. F is the outside, g is the inside. In this particular case, I do f outside, g inside. Example 3, so I have x minus 5 cubed plus 1 being h of x. I want to decompose it into two functions so that one is inside and one is outside. Obviously you can see x inside is this part, right? So I think a very natural things to say would be x become x minus 5. Now there's multiple way of doing it. I just choose to do it this way. And then after this, then I'm going to cube it and then add 1, right? And then we'll have x minus 5 cubed plus 1. But this is the placeholder of this. So I would write g of x is just my initial map, which is x minus 5. But what is f of x? F of x, I take these things, I cube it. So actually I would say I'm going to cube this and then add 1. So that is my f of x. This is function decomposition. You have to recognize what is inside and what is outside. So the next part is application of functions. So using composition. So for example, I know area of circles is pi r squared. R is the radius, but the radius is not a number or something that I plug in. It's actually changing by a formula related to time. So at different time, the radius changed by 4 minus square root t. So write this function with respect to time. So what I'll do is I would do 8 of t would equal to pi. Whenever I see r, I just plug this 4 minus root t square. So this would give me the area at different time. So this, we use this term with respect to time. So you can see right now my input is time. After I input it, I will calculate the area. So this is the function. What is the domain of this function? So for time to work, first of all, this has to be positive, right? So time has to be positive. Can time goes on forever? No, we don't want to have a negative radius, right? So 4 minus square root t has to be positive. This radius has to be positive. It doesn't make sense to have a negative radius. So the highest t that you can get would be 16, right? So t must be less than 16. Otherwise, you have a negative radius. So the domain would be from 0 to 16 second or whatever time period. The second one is a very popular work problem situation where you have a square paper 10 by 10. So this is 10 unit and this is 10 unit. They didn't say if it's inches or feet or something. They cut off x values of a squares in 4 corners and then fold it up. So after you fold it up, it would be like a box without a lid on the top. So it's like this, right? But so the height would be the square formed by you cutting it out. And what would be the side length be? Length and width be? This would be 10 minus 2x, right? Because you cut off x, 10 minus 2x. So what is the function of what is the volume? The volume V of x would be equal to x times 10 minus 2x square. 10 minus 2x here, 10 minus 2x here, and then an x. Length times width times height. So this would give you the function. The next part is symmetry of functions. So functions, after you graph it, there's the two particular types that is very interesting or useful in like chapter 5 when we are looking at certain, actions of calculus. It turns out that if we know that the function is an even function, that means it is symmetrical over the y-axis. So these are just names. Symmetry means about the y-axis means it is the same if you look at left and right, with y-axis being the axis of symmetry, and we call it even function. Odd function is when it is symmetrical about the origin, meaning if you copy this on a piece of paper and you turn your paper upside down. This is a screen. I can't turn it upside down, but well, I guess I can. You would notice that it's the same thing. Okay, so how do we check that if I don't graph it? The algebraic test strategy is if it's an even function, f of x and f of negative x is the same height. So they're identical. And if it's an odd function, because after you turn it over, they are actually the same thing. F of negative x is negative f of x. So what you do is to check whether it's even and odd is evaluate f of negative x and see if it is exactly f of x or the opposite of f of x. So let's do a field function. Maybe we'll just do a and b to see if these are even or odd. So the first is f of x is x to the 4 minus 2x squared minus 3. So I want to check if it's even or odd, I want to do f of negative x. So it will be negative x to the 4th minus 2 of negative x squared minus 3. If you do an even root of any variable, it becomes positive, right? The negative goes away. And minus 2, this is also even power, not root, even power, x squared minus 3. So is this exactly f of x? Oh, this is exactly the same as f of x. So f of negative x is exactly the same of f of x. So that's even. That means it is an even function. I call this function an even function. Okay, just jump off the screen. Then let's do the second one. G of x is x cubed minus 4x. In both cases, I'm going to just do negative x. So it will be negative x cubed minus 4 of negative x. So negative x cubed is negative x times negative x times negative x is actually negative x to the cube. What about 4 times negative x is plus 4x, because this negative 4 times negative x is plus 4x. And did you see that this is actually exactly negative of x cubed minus 4x? That is negative f of x. That is exactly the original g of x original G.